Have you ever stopped to wonder how your phone can recognize your face, or how apps can translate languages in, real time? The magic behind all of that is deep learning. Today, we're going to jump right into its core concepts. We're using the legendary textbook by Goodfellow, Bengio, and Courville as our guide to really break down the essential building blocks that make these incredibly powerful systems tick. Okay, so here's our roadmap for today. We're going to start with the big picture promise of deep learning. Then we'll get into the language it speaks. After that, we'll look at what the machine is actually trying to do, how it learns, what its architecture looks like, and then at the end, we'll tie it all together. So, let's start at the beginning. What's the central idea of deep learning? Well, it really boils down to this incredibly powerful concept: learning in layers, building up complex understanding from very simple pieces. And this quote from the book just nails it. See, in the old days, human experts had to painstakingly tell a computer what features to look for, the edges and corners of a face, for instance. Deep learning just completely flips that on its head. The model discovers these useful patterns and representations all by itself, learning to see complex things by building on simpler concepts, layer by powerful layer. And what's fascinating is that this isn't some brand new idea that just appeared out of thin air. Deep learning is actually the third and by far the most powerful wave of this kind of research. It's standing on the shoulders of giants, building on decades of progress, from the early days of cybernetics all the way through the connectionist movement of the 80s and 90s. So, how do these models actually learn to see the world in this layered way? Well, to get that, we first need to understand the language they speak. And that language, at its core, is mathematics, specifically a mix of linear algebra and probability. The most basic word in this whole language is the vector. Just think of it as a list of numbers that represents one single thing. So for example, in that famous iris flower dataset, you could have a vector for one flower that lists its petal length, its petal width, and so on. Each of those numbers is a feature, and together they define a single point in a kind of high-dimensional space. Okay, so what if you have a whole dataset of flowers? Well, you just stack all of those individual flower vectors right on top of each other, and what you get is a matrix. In machine learning, you'll often hear this called a design matrix. It's super simple. Each row is one flower, and each column is one feature. It's just a crazy efficient way to organize data for a machine. Now, you'll see symbols like these all over the place. Don't worry, we're not about to have a pop quiz on linear algebra. But it's really useful to know that these are the basic tools the model uses to manipulate data. They let the network stretch, combine, and measure the data as it flows through. And that's absolutely essential for the whole learning process to even work. But it's not all just about manipulating numbers that are set in stone. Deep learning has to deal with uncertainty all the time, and that's where probability comes in. A really key concept here is something called Shannon entropy. You can just think of it as a formal way to measure surprise or unpredictability. When an outcome is almost certain, like close to 0 or 1, the entropy is super low. But when things are totally up in the air, a 50-50 shot, that's when entropy is at its absolute highest. Okay, so we've got this mathematical language. What's the machine actually trying to do with it? Well, the ultimate goal isn't just to memorize the data it's already seen. That's easy. The real trick, the whole point, is to generalize from that data so it can make accurate predictions on new stuff it's never seen before. So we measure this with two key numbers. Training error tells us how well the model did on its homework, the data we gave it to learn from. But the test error, that's the final exam. It shows how well it performs on new data out in the real world. And the big goal here is to make that generalization gap between the two as small as possible. This all leads to this critical balancing act. A model's capacity, basically how complex it is, has to be just right. If it's too simple, it can't even capture the real patterns in the data. We call that underfitting. But if it's too complex, it might just memorize every little detail, including all the random noise, and then it'll fail miserably on new examples. And that's called overfitting. The name of the game is to find that sweet spot right at the bottom of the curve. And there's this classic philosophical idea, Occam's razor, that is basically our guiding star here. It says that if you have a bunch of explanations, the simplest one is usually the best one. We want a model that's just complex enough to find the real pattern, but not so complex that it starts making things up by memorizing noise. When it comes to generalization, simpler is almost always better. So how in the world do we find that perfect, just right model in that sweet spot? Well, we do it through a kind of guided trial and error, this process of gradual improvement that we call optimization. And the absolute workhorse algorithm for this is called gradient descent. Here's a way to think about it. Imagine you're standing on a huge, foggy mountainside, and your goal is to get to the lowest possible point in the valley. The gradient tells you which way is steepest up. So what do? You take a small step in the exact opposite direction, downhill. You just keep doing that step by step, and eventually you'll find the bottom. But, of course, there's a catch. In the crazy high-dimensional landscapes of deep learning, it's not just about simple hills and valleys. You could get stuck on something called a saddle point. Think of it like a mountain pass. If you look one way, it goes down. But if you look the other way, it goes up. The ground is flat right where you're standing, so the gradient is zero. You think you're at the bottom, but you're actually not. Navigating these tricky spots is one of the biggest challenges for modern optimizers. Okay, so we've got our data, we've got the math, and we've got a process for learning. But how are these pieces actually assembled? This brings us to the model's architecture. And the most fundamental type is the feed-forward neural network. Now, let's talk about the name neural network. Well, it's kind of inspired by the brain. It's honestly much more accurate and helpful to think of these things as really powerful and flexible function approximation machines. Their goal isn't to perfectly copy a biological brain. It's to achieve statistical generalization, and they're guided by the hard principles of math and engineering. And here's what a simple one looks like. Data, our vector x, comes in one end. It flows in one direction through one or more of these hidden layers. That's where all the magic happens, where those crucial representations are learned. And then, finally, it gets to an output layer that spits out a prediction. The connections themselves are just matrices full of numbers or weights that get tweaked and adjusted during that learning process we talked about. All right, we have covered a ton of ground. Let's take a step back and pull all of these building blocks together to really see the big picture. So when you boil it all down, deep learning isn't just one single magical idea. It's really this powerful framework that weaves all these concepts together. You're learning representations from data, using the language of math. Your goal is always generalization, trying to avoid overfitting. And you achieve that through an optimization process like gradient descent, all happening inside a layered network. It's this powerful combination that lets it solve such incredibly complex problems. And that leaves us with this final massive question. We've seen that the heart of deep learning is all about building useful representations of the world from data. Now, we can use those to make pretty amazing predictions, but can these learned representations ever lead to something more? Something like true human-like intuition, or maybe even genuine creativity? That's the exciting journey we're all on. Thanks for joining me today.